I think we're good. I think it's recording.
Okay. So just a start.
Yeah,
Yeah.
I think so.
All right, everyone. Okay, so this is Peggy, and I'm from University of New South Wales School of Material Science and Engineering. I'm also Women Fleet Fellow from Fleet. So today I'm going to introduce our recent works like in
I think she's just checking if the microphone can be heard on Teams. Yeah, okay, that's what she's doing.
Sure.
Keep on talking.
Okay. All right, so yeah, thank you again for coming to my talk. And today I'm going to talk about the research we have done in the past like 5 years, which is engineering the ferroelectric bubble nanodomains and analyzing figure structures. And okay, so this slide just summarize the work from our group. So our group is led by Professor Nagi UNSW, and the main work is about like by engineering the ferroelectric oxide interface, and we can tune the domain structures of these ferroelectrics and also its properties, and to realize its some desired like electric functions. So we have a bunch of lab facilities like the POD to build like really decent thin films filter structures. And then we have the scanning probe microscope, which I'll talk a little bit more later, which is very key tool we use to characterize these ferroelectric materials, to visualize these domain structures, and we can also manipulate these domain structures using this technique. And then recently we also get a low temperature probe station, which can help us to do some transport.
It's okay.
Just testing it. Keep on talking.
So yeah, so experimentally, this work has been done in our group based in UNSW. The leaders Nagi and also myself and Dr. Shangavithan has been a lot. We've actually just finished her PhD this year on this project. And we received very strong support from our theoretical team from University of Arkansas, which is led by Professor Lauren Malaysia. Also, we have collaborated with quite a few global universities on the like TEM categorizations and also the freestanding memory of these ferroelectrics. Okay, so in today's talk, I'll first introduce the ferroelectricity and the domains and how we use the scanning probe microscope to do the characterizations, and then I'll introduce the topologic defects that we have discovered and researched in the last few years, and also I'll talk about like the stability conditions of these nanoscale bubble domains, so that we can better to manipulate it. Okay, so first, what is the ferroelectrics? So ferroelectric has two key or critical features. One is it has spontaneous polarization, and another one is this spontaneous polarization can be switched at the external electric field. Okay, so for example, here shows typical perovskite barium titanate crystal structure here, and in this structure we can see that the center atom, the titanium, is actually not located at the center, is slightly offset. So this gives it a like dipole in this structure, which for this spontaneous polarization. Okay, and then actually at this position, it shows the lowest energy, so it can stabilize at that. And this spontaneous polarization can be switched under external electric field. So it's from this low energy position to the other one, and both will give this spontaneous polarization. Okay, so these two shows two different spontaneous polarization direction.
I'm sorry, can you interrupt? I'm just going to have to exit out of the screen because the audio is not working on Teams.
Oh, okay.
So people are going to miss what you're saying.
Okay.
So I'm going to connect via your laptop, and we're going to I'm trying to mute this screen.
So now it's okay. And my microphone is on. Okay, so
Yeah, I think you can.
can you hear me from the Teams?
Well, I've got the audio off, so. Start talking, Peggy, as it's using your.
Okay.
Yeah.
Yeah.
Yeah, that's good.
Should be
Okay.
fine, yeah.
All right. Okay, so yeah, so basically like in the ferroelectrics, if in this perovskite structure, it can give this different spontaneous polarization directions. All right, so so this so how the domain forms, which I this is when it has this spontaneous polarization, and in these materials and at the interface, it will form these bound charges. Okay, so the boundary charges will give its depolarization field, which has the opposite direction of this spontaneous polarization. And to minimize this electrostatic energy of the depolarization field from that interface, what will happen is this material will just the domains will split into this up and down 180-degree domains. Okay, so this will shows like opposite direction of the spontaneous polarization, and it forms this 180-degree domain structures. And in another case is, for example, is this material is formed under very strong strain or condition, then to relax this elastic energy, then it will automatically like form this kind of ferroelectric, we call this 90-degree domain structures. So it has an out of plane and in plane like a polarization direction. Okay, and how we can visualize these domain structures, we use a technique called piezo response force microscopy. So in this, by using this technique, we just have a conductive probe and scanning on the film surface and applying under AC bias. So when to apply an AC bias, this material, like the certain atoms, will has a vibration, has the same frequency as this AC bias, which will also give it the material has a deformation, because the ferroelectric is also a piezoelectric material. So it has a deposition, like the deformation in response to the external electric field. And this kind of change, the shape changes actually has the vibration has the same frequency as the input drive voltage, so the AC bias. So what will happen is the up or the down polarization domains will actually show in phase or out of phase response, like in response to this AC bias. Okay, so by extracting these in phase out of phase informations, and we can get these phase images from the PFM, which shows like two opposite contrast. Has like, so these different contrast colors shows that these two areas has different domain structures. Okay. And another very key information is the amplitude. So the amplitude, it shows how strong this piezo response is. Like under this AC bias, how strong the deformation happened. So this is called electromechanical response. Okay, so these two informations can tell us like the domain structures, and also like if it's like a piezoelectrical, if it has a piezoelectric or the ferroelectric response. Okay. So, and also the scanning probe microscope has a lot of other functions that we can use that to check the topography, like the roughness and morphologies of the film surface or material surface. It can also to check the domain structures, not only the ferroelectric, but also if we use a magnetic probe, then it can also give us the magnetic domain structure information. And if we use a conductive probe, we can also get the current map to understand the conductivity of the film surface. And it can also use to study the surface charge and the potential and the work functions of the materials. And recently we also used developed one called tomographic atomic force microscopy, which I will also introduce a bit more later. It's just that basically we can use a very hard tip to remove the surface of the material, and then to study like the features of the materials after removing the surface. All right.
Becky, is it one instrument with different probes?
Yes. So it's basically like using this one tool, just by changing this mode or by changing, like select a correct probe, and we can use that for different functions. Like, okay, so it's a very powerful tool for the material study. Okay, so So we can see that the ferroelectrics has these domain structures, which is very similar to the well-known magnetic materials. So magnetic material has been used as a storage for a long time. And also people always trying to increase this, like the storage densities. So for example, by by decrease the domain size. And then I think it's about like 10, 20 years ago, they also just has a huge progress. It's just by changing the directions of the magnetic domain orientations from the in plane to this perpendicular. Okay, so same as this ferroelectric materials. So ferroelectric also has these domain structures, and it also has been used to like develop these ferroelectric storage functions using the SNDM. And in addition, and ferroelectrics actually, because it's about the electrical polarizations, and it can link more about the electricity like properties, and it has shown some very like low emergent properties. So for example, for the BFO, the domain was, some of the domain was shows conductivity. And 5 years ago, and we developed a domain wall memory device that we just use this conductivity of the domain walls, and we can, using this device, and then we can create and remove these domain walls to form like an open and short circuit. So to realize the switch on and off for this memory device function. Okay, so the problem is if for the memory or the storage functions, and we know that it's already like approached this size limit. And also it has like the heat death, which just has a really get really hot when the device is working. So is there any solutions that we can develop like a higher density and with lower energy, like these kind of solutions? And recently, and maybe like in last 10 years, there are a lot of studies have been put on these topological structures, either in the magnetic and the ferroelectrics. So you can see these domain structures is, especially for the ferroelectrics, it shows quite different configurations as the one I showed before. Like the conventional ones shows the 180-degree domain structures up and or down, and all the 90-degree domain structures. And these ones shows these topological structures, and which could have some see like some normal functions. And actually this has been studied a lot first in the magnetic materials. For example, like the magnetic skyrmions has been found that these skyrmions can be get like really small, and it can be manipulated at the magnetic field. And also there is type of device has been realized by, they can actually create these magnetic skyrmions and move it by applying or by tuning this applied bias pulse. Okay, so then let's move to the ferroelectrics. And we can see that in ferroelectrics, the size, it also has been reported in a few like in a lot of like ultra thin heterostructures, and the size of these topological defects structures is as small as like 5 nanometers or even smaller. So we can see that the smaller size, that means it has a potential for a high density function. And also it has been found that these, like for example, at this vortex core, and these kind of materials show some emergent properties like the high conductivities. So that means it has a smaller size, and also for ferroelectrics, it can switching at a really high frequency. So it means it has a high speed processing potentials, and also because of its really small size, we can operate it at a really low input electric field. So that means it gives us a very promising perspective of this ferroelectric topological defect that we can use that to develop a new type of electronic devices with all these features. Okay. Then next we just focus to the one we have been studying last few years. It's called the nanoscale bubble domains. So this type of domains is actually first discovered or first reported by theoretical publications in like 2004 and 2006. So it's about like 20 years ago. And they found that in a compressive strained PZT film, and if it's under a proper, like a critical depolarization field, it can form this kind of nanoscale domains, which is kind of like a transitional state between a monodomain and conventional membrane domain. Okay, so how can we realize this? We, after like this 15 years, and then we trying to realize that experimentally. We prepared like PZT films on the LSM-OSTO substrate, which is under a compressive strain. But at the very beginning, it shows this monodomain structure. All right, so we need to tune in its depolarization field. What we have done is we insert a STO dielectric layer between two PZT. So what will happen here is actually this introduced two interfaces at this PZT layer, and this will get some boundary charges at this interface and introduce a depolarization field in this system. And as a result, we're very excited to see that after introduce this STO layer, and then we can see these nanoscale domains shown in our film. So yeah, it's like exactly like what happens in this theoretical work. Okay, then if we have a close look at this film, and we can see that this kind of nanoscale domains is uniformly distributed in this film, and the size of it, if it has a close look at that, we can see is less than 10 nanometers. So actually 10 nanometers is also kind of a size limit by using the scanning probe microscope, because the probe size is also around this like 10, 20 nanometers. Okay. And then we did the TEM on using the displacement map to check the polarization directions. And we can see that. So here shows the phase image, and we can see it has this black and the brown yellowish color. So this shows two different polarization direction. And the matrix is actually like shows a downwards polarization, and the black one says upwards polarization. And then we can see that so this can also be found like observed in this TEM, which shows the downwards in the matrix area. And in some areas, we can see that this upwards domains is actually shows this tilted polarization structure. It's not like perpendicular as the 180-degree domains. So that's become interesting. And then the simulation work shows that under these conditions, this kind of tilted polarization shows the block in the near-like domain on the dipole rotations. And then why this, or like how we can use this technique to like distinguish, like if it is the conventional or it is like the topologic bubble domains. So we just have a look at this image that we can see there are two different type of domains. So one actually is the conventional cylindrical domain, which has this, you can see the circle shape, and it has a very clear domain wall, which shown as black in this amplitude. And there is another type of domains which shows like a fuzzy domain structures, which is very blurry. So this is because this up and down domains, so show the 180 domains, we give it very clear domain wall. And at the wall, actually, there's no piezo response, so it gives 0 amplitude. Okay, and the phase will give a very clear 180-degree domain, like the phase difference. But for the bubble domains, because it shows this tilted domain structure and there is no very sharp domain walls, so as a result that we can see that the amplitude will not go to 0 actually, and also the phase difference is less than 180 degrees. To verify this, actually, we also have done some experiment. So first we clear the domain area, and then we created the different type of domain structures under the bias pose. And if we just these domains are formed under different pose width, so it's like this one's formed under 0.5 seconds, and we can see that it's a very typical cylindrical domain, which shows the cross section of the amplitude shows a W shape. That the inside and outside these domains shows a high amplitude, and at the domain walls, it's reach the bottom. Okay, so it's keep shrinking when we decrease the pulse width. And at some point, we can see that it's become like one dot. So it's quite similar to the bubble domain or nanoscale domains. But we can see that the center of these domains shows also a very, very small amplitude. And if we keep reducing the pulse width, we can see that there is one small domain shown here, but it has actually a higher amplitude. So what we think is this one is actually also included. So it's shown here, has some domain wall structures. So maybe what we can see is a very, very small conventional cylindrical domains, but the tip can't distinguish the wall and the domains, so that it shows a really low amplitude. And for the bubbles, because even at the center, it still shows this tilted polarization, and there is no clear domain walls. So as a result, it gives us a higher amplitude. So yeah, so use this one. We are confident that we can use this tool to identify or distinguish these nanoscale bubble domains or the domains with topologic configurations with these conventional domain structures. Okay. And we also check this properties. So for example, this because it has this tilted polarization, it can give a higher electromechanical response. And we did apply the bias cycle. And we can see that from 0 to the point 1 to 2, so which is from the nanoscale bubble domains to the matrix, it switched from this tilted domain to a downwards domain. And this gives a really high amplitude response, or the piezo response, electromechanical response. And then in the next cycle, and then at this point, it's already changed into this conventional domain. And in the next cycle, and then we can see that same from the 0 to the -4 volt, it gives a much lower response. So this one, we can also confirm that there is a structural difference between the bubble domains and the conventional domains. And another properties, very exciting properties we found that is this nanoscale bubble domains shows the high conductivity. So we can see that this is a bubble domains and which gives a high current. So this one is a conductive AFM. We get this image by scanning the surface under constant bias, and it will give a feedback of the current of this scanning area. So we can see that this area shows a high conductivity, which is corresponding these bubble domains. And then we also think, because I mentioned that for the BFO films, it can, the domain walls can show this high conductivity. So we just created this cylindrical domain, and then we found that, okay, these cylindrical domain areas shows nothing. So that means this high conductivity is not because of the domain wall. And this also show us that, okay, our domains, because I mentioned that our domains has no clear domain walls. So this means that first, the domains has no domain walls, and also like the domain walls actually gives no response. Okay. Then, yeah, so next week, just can take a break by enjoying this beautiful images from the James Webb. This is a powerful, telescope that gave us these really beautiful images. And when I first see that, so okay, yeah, it's like really amazing. And then when I enjoyed it for a while, I feel like, oh, it kind of look similar. So I made like images like this, and I see like, okay, there must be some physics between these two, like similar, but I don't know. I don't know that there's a link between the light year scale and or the nanometer scale. But I know that in the light year scale, pretty much we can do nothing. Everything is out of control. But in the nanoscale world, we definitely can do something to control it, or maybe to understand it. Okay. Then, yeah, so
before you go on,
yeah.
So is the goal to be able to control the properties and structure of the domain walls and bubbles?
Sorry,
Is this the goal of the research?
Yeah.
Is to be able to control the structure and therefore the properties?
Yeah, that's what we're trying to do. Like, so to see how we can achieve these domains and how we can manipulate that. So once we understand all this, then next, I think it's more confident to develop the devices, and so we can see what we can tuning these properties. Right?
Oh, yeah. And the PZT material that you use in the work.
Yeah.
Can you get the same domains using another film?
Yeah, that is in my last slide.
Okay.
Very recent findings in our research. Yeah. Okay. All right. So first, as Tiklanda said, that we like the purpose of the goal of our research is trying to control this. But to control this, the first thing is we need to understand it, like to understand what determines these topological defects. At the very first few slides, I mentioned that the theoretical work found these nanoscale bubble domains in a compressive strand PZT film under like a critical depolarization field, right? So why that strand and the depolarization field is important? This is because, so first you can see at the A and B, it shows like materials with two different type of electrode. And we know that it has a spontaneous polarization and these boundary charges, and which will form the depolarization field. But if we have like ideal electrode, then all the boundary charges will screening. And in most of the case for the real electrode, these boundary charges will remain the interface, and this will form these potentials and the depolarization field. And this depolarization field will like become more significant when the thickness decreases, right? Okay, and so like in the film, for the tetragonal films, which shows like out of plane polarization, spontaneous polarization. If it's under a compressive strand, what will happen? You can imagine it's just to pull this the crystal structures, and this will kind of like stabilize this out of plane polarization. And on the other hand, this depolarization field is kind of to kill these polarizations to cancel the spontaneous polarization. So at some point, to decrease this or to minimize the effect of the depolarization or the energies from the depolarization field, it will try to form these 180 domains. But at a critical point, it will just push that too hard and to form its like in-plane polarizations. Okay, so this will form the polarizations actually to curling. Okay. So all these curlings is a result of this epicapital strain stabilized on the outer plane and the depolarizations, which is trying to reduce it. So this is kind of like very like the stable conditions of this topologic like configurations with this curling polarization. Okay. So that means there are like two very important boundary conditions, the mechanical and the electrical boundary conditions. For electrical boundary conditions, it can be tuned through this epitaxial strain, and it also like the external stress applied by the maybe the probe and the bendings, it can also change this boundary condition. And for the electrical boundary conditions, one key thing is the depolarization field. So these can be tuned by the interface screening condition and also the film thickness, which also determines the electric field, right? And also the temperature can also affect the screening conditions. And another is we can also apply external electric field to change this, like the electric boundary conditions. So this is what we trying to see, that if we can use these factors and to achieve or to manipulate these bubble domains. Yeah, so the first thing is how can we like achieve that? If we have Lambrin's domain, and how can we obtain these nanoscale bubble domains? So this is recent work we just accept. The paper just accept like 2 days ago. Is we also collaborated with our theoretical team, and this is a simulation work which shows that when we have this Lambrin's domain, and if we applied a stress or increase the screening and decrease the thickness, it all can push these the Lambrin's domains towards these nanoscale bubble domains. And we can also combine this all these input factors and to further tuning the size of these nanoscale bubble domains. All right. So experimentally, then I trying to show the evidence of this simulation work. Then I use a technique I mentioned before. It's called tomographic atomic force microscopy. So here is use this scanning probe with a very hard coatings at the tip, which the one I use is with a diamond coating. Okay, so this diamond coating, with the diamond coating, when we're scanning at this surface under like by changing this deflection of the tip, it can actually remove the surface of these materials. And because the diamond is also conductive, so we can actually immediately switch that to the PFM mode to image the domain structures right after remove the top surface. Okay, so that is we can obtain these two images, which is before removing the surface and then is after removing the surface. So this one is these two differences is under a force, and also it like changing the thickness. Okay, so we can see that. So this image shows how the domain changes with the removing of the top, like the materials layer by layer. And we can see that this Lambrin's domain can start to shrinking into these nanoscale domains. And we can see that it still shows like really high amplitude, as I mentioned, so which we believe it has these tilted topologic configurations. And then at some point when we remove this STO layer, And then we can see that is go back because STO Lager said is also introduced the depolarization field. And then after that, the electrical boundary conditions also has a sudden change. But then when we just keep reducing the thickness, then it will start to, the domains will start to break and also shrink into this nanoscale domain again. So we can see that, okay, this is actually matches what we found in the theoretical, that with the decreased thickness and under the stress, the domains are actually changed from these membranes to these nanoscale bubble domains. So this is one way that it's also like can be a guideline for us to get, for example, at which thickness we can obtain these nanoscale domains. So it's very interesting that we want to see that if it can be used like a universal guideline. So I prepare like 2 films, which one is used with this STO spacer and another one is without the spacer. So for this sample is has a different composition, so it's not a scroll bubble domains. I need to mention that, okay. And then we find that if you have a let's compare these 2 image. So for both, it has a force and on top of like single PZT layer. So this one is after we remove the top surface until reach the bottom PZT. So basically at this interface, the conditions is exactly the same. And then we can see that domain structures is also kind of similar with this short membranes or short membranes domains and also these nanoscale domains on that. So yeah, based on this, we think that even we have conventional domains, and there is a way that we can try to tune its like thickness, and then use these techniques to find like conditions to reach or to achieve these nanoscale bubble domains. Okay, another one, this is also a work based on the theoretical work that in this work, what they have done is we just keep the sample at above the Curie temperature. So above the Curie temperature, the ferroelectricity disappears. Okay, and then when it's decreased to the Curie temperature, the ferroelectric domain will start to form. So what happens if we quench these domains to a low temperature and under the different electric field? So this will change its very initial like electrical boundary conditions when it form the domains. And we see that, okay, if there's no electric field, then it will form like up and down domains, maybe like the ratio is 1:1. And then if it's quenching at a high electric field, and at some point it can also form these nanoscale domains. Okay, so this can be also a way that can reach these nanoscale domains at a low temperature and for some applications. Okay, so yeah, so far like we have some ways to, if we have like Lagrange domains, we have some ways to get these bubble domains, and we know that how we can achieve these bubble domains by tuning these boundary conditions. And how about like manipulate it? So this is actually from my first work, like we find when we actually to image these bubble domains, and we find that these domains is quite sensitive to even the AC bias, as low as 100 millivolt. So this one shows that like 300 to 600 millivolt. The domains can change from this nanoscale bubble domains like into these cylindrical domains. So that means even under really low electric field, low input, the domains can evolve. So maybe you can also like use that for some low energy device ideas, like which can operate as low as a few hundred millivolts. Yeah, and then another is to change the domains, we can also, the mechanical force can change it from the Lagrange to the bubble domains. And we can also use the mechanical force to erase these domains, like to clean it. If we, for example, develop a device, we can also like, there's another additional ways that we can clean these domains. So we can see that, and we can also recreate it then by apply this the bias pulse. So this is what I just introduced at the very beginning, that at this point, with a really small, really low pulse width, and we can form these nanoscale bubble domains again. Okay. So this can also be like repeated, remove and recreate and remove again, which is also very good for the device function. And another one is to think about like further developed for example, for the semiconductor industry applications. Also last year we published one paper is on the freestanding ferroelectric bubble domains. So it's actually we can remove this LSMO layer and get this freestanding ferroelectric films and remove that to the silicon substrate. So this is also like a milestone that we can transfer these domains to the silicon, and there could be like a wider applications. But one thing at the beginning that we think when we transfer, remove this from the substrate. So one thing is the clamping from the substrate we gone. So the mechanical boundary conditions actually change, right? The compressive strain probably gone. But what is interesting is when we just transfer that and we see that there is roughness. So at these curves actually can provide this compressive strength to the film. So it can maintain the bubble domains at these areas when it has this compressive strength. So this is
after the transfer.
Yes, this is after the transfer. So we can see that these domains can still remain, especially when it has this the areas which give it like the so this will provide this compressive strength or maintain the strength conditions there. Yep. So basically, so this slide has summarized how we can actually manipulate this nanoscale bubble domains. Actually, we can realize that from the electrical input, we can tune it just between the bubble, cylindrical, and matrix domains with the electrical bias, and also or the mechanical input. And also we have kind of like a thorough understandings of how we can reach the desired topological defect by tuning these key factors. Okay. Yeah, so in addition, I also would like to introduce a few of our other recent works. And one is we have just written a invited perspective, which is submitted to the Nature Materials, which is under third revision, so it's very promising. This is on the spherical ferroelectric solitons. So in this perspective, we gave a very thorough summaries of like 3 typical ferroelectric topologic solitons, the skyrmions and bubbles, and another one is called Hopfians. Also, this year we also published one paper on the room temperature ferroelectric resonance tunneling junction. So this one shows like at a room temperature, these ferroelectric heterostructures can show this the lective differential resistance, like which is due to this resonance tunneling. Okay, and so this one is Tiklan also asked if we can just find that in other materials. This one's still like in submission, which is also very exciting work that we find this kind of solitons, because it's in the BF4 STO superlattice. So this is lead-free, which could be more like environmental friendly. And BFO is also multiferric materials. So that means we could have another more channels to tune these materials. This is just the beginning that we first think, and it's like the first observations of this ferroelectric solidants in the multiferrics. So yeah, very exciting work. Okay, yeah, that's all about my work, and thank you again for coming to my talk. Welcome some questions. Thank you. The stability? Yeah, it's pretty much the same. So this slide also summarized that. So also BFO, the difference become BFO is BFO at bulk structure. It shows the rhombohedral. So the polarization direction is in the 111 direction instead of 001. And then in these conditions, because we use the LL, which has a much smaller lattice parameter, which can provide it stronger epitaxial strength. So this is also just make it stabilize its, or just tilted its outer plane polarizations towards like 001 orientation. And in addition, like this STO BFO layers is also because of the polarization mismatch, it also can stabilize, like provide like make the STO because it's non-polar and in this superlattice, and it gives it like the mismatch strength give its polarizations. And the same that the depolarization field also play a critical role that it can try to curling the polarization structures. Yeah, and also we can see that we can actually observe different type of the topological configurations in this film. This one shows like the TM, the displacement map, like to show how the configuration look like. Yeah, I think this is a plan view, so it's on top. Like you can see that from the top of the film. Yeah, and we can see that the size of the domains is around maybe 3 nanometer. So, which is very, very good.
Soliton, a general term to describe all of the ferroelectric.
Yeah, actually, I checked that. It's like topological solitons. They also call topological defect. So it's, yeah, basically which shows these individual structures different from the matrix.
Did you also try to vary the spacer layer as well?
Yeah, we did. Yeah. So yeah, have a lot of like backup. So for example, here we tune this spacer layer, because also the spacer layer, when it's getting thicker, the screening will getting weaker. So it also like change the boundary like conditions, and it can change this domain structures. We also started like fix the spacer layer and change the thickness of the PZT. And then you can see that this is like from the very beginning of the fabrication, and then how we can realize these smaller domains. Yeah. Right. Thank you, Tikle. Good questions.